So I was asked by the group to kind of verbalize what our standard operating procedure is, what we do to get the assessment and the remediation right. So this is what I came up with, kind of looking at our 30 years of experience. Consider your goals, corporate directives, what's the risk tolerance, stakeholder and community concerns. Number 2, next, develop a robust conceptual site model. And what I mean by robust is that one that people will not pick holes in, that you've got enough independent data to be really sure about what's happening in the subsurface. Next, please. Consider the regulatory conditions. Sometimes the regulations change, and that will help you to achieve remediation quicker and cheaper. And that's what one of the things Jeff is going to talk about later on. Next, please. And then we present our recommendations to the client and whoever we need to do, if it's a litigation, mediation, or regulators. Next slide, please. So one of the things that we found is that remediations fail because people misinterpret their site. Maybe it's the geology they got wrong, maybe it's the groundwater flow conditions, maybe it's the distribution of chemicals. So we put together last year a list of 29 potentially costly soil and groundwater mistakes that are fairly common, some of them not so common, but we outline these mistakes that people make in characterizing the site, which results in a problematic remediation. And the next slide will show you some of those, and they're different sizes because I just pulled them out of this document. So one is faulty phase one investigation, where somebody has missed something in the phase one, like a tank was missed or not documented or something like that. And that happens. Next, please. Incorrect determination of groundwater flow direction. This is the basics thing that you teach in Groundwater 101, how to figure out which way the groundwater is flowing. But sometimes people get it wrong for various reasons. Could be surveying, it could be just they don't know how to do it properly, could be that they haven't defined all the aquifers, that sort of thing. Next, please. Failure to identify multiple aquifers, that goes back to 7. And the case study that I'm going to do following this introduction is the case of that, where there were 2 water-bearing units. The original consultant didn't recognize that were 2, and they were vastly different in the direction they were flowing, and that had major implications on remediation and litigation. Next, please. Inadequate horizontal delineation of impacts. So have we put our arms around it? Horizontal delineation, vertical delineation. You need to know where the contamination is and the distribution within that. And then contouring gone wild. This is kind of my saying, and it's kind of related, number 20 there. It's when you use a program like Surfer, which is a contouring program, without considering things like geology and hydrogeology. And Surfer, you can just tell it how to contour, but you're making an assumption about, say, concentration variations between 2 known points. And that could be a linear concentration variation, but it also could be something different. So you're kind of dealing with the output from Surfer, which may not give you a representative indication of the distribution of contaminants, but it makes nice maps. Next slide, please. So this is the first case study I'm going to talk about. We worked on this for a client for a number of years because that was the best way to go about it for them. So this was a property transaction where our client, which was an international company, bought this site that had TCE on it, and they had 5 years to prove what the costs were related to that TCE. There's very short timing left because their consultant used up 4.5 of the 5 years allotted for this. And that consultant came up with the recommendation that you do pump and treat, and that was about $8 million. So the client kind of got their attention, $8 million, and they asked us to do a peer review. And not only was it an expensive remediation, but there was a residential subdivision to the east or to the right of this site where the people used groundwater and it was contaminated with TCE. So our property was a source, the neighbors had TCE, and the regulators were involved, so it was not a good thing. And then later on, the client decided to decommission this plant. They wanted us to be involved in the decommissioning, and that allowed us to kind of just clean up whatever we couldn't get at before. Next slide, please. So the problem with this site was the conceptual model, and the conceptual model's on the right, and the lighter colors on the sides show the aquifers or the water-bearing materials, and the darker colors, I'm colorblind, so it's relative to me, show the aquitars where the groundwater couldn't move. And basically, the previous consultant had not recognized that the top aquifer and the lower aquifer were two separate things. So they totally misinterpreted the groundwater flow direction, which they had going from west or left to east or right into the subdivision. And because they were totally different aquifers, they came up with a tremendous velocity and contaminants moving towards the residential subdivision in the east. So this was not a good situation. But what we did was we did a very quick, intensive investigation of the site, recognized there were two separate aquifers, and came up with this conceptual model. And we're able to, with that conceptual model, determine, Chris, if you can advance to the next slide, please. Oh, that's good. Before I go on with that, we also did some lagoon remediation. Next, please. And some landfill remediation. Next, please. And we demonstrated that our client was not responsible for contamination in the subdivision to the east. There was actually a similar plant, different owner further east that was responsible for that contamination. Next slide, please. So we were able to determine what was moving off site and where. And basically what it was our client was responsible for didn't move off site. It actually evaporated on site. And we were able to get a limited industrial risk-based closure. And this was in Michigan, one of the first ones that was allowed. And it basically resulted in just really monitoring for our client. Next slide, please. So we were able to show there was no need for pump and treat. We were able to monitor at a frequency, and that symbol is proportional, alpha, to the transport rate. We did a groundwater model to see how quickly the chemicals were moving, and it allowed us to design a monitoring frequency that was meaningful relative to how quickly the chemicals were moving. And we did monitoring for a number of years at about $15,000 per year. And then later on, when our client wanted to decommission, we were able to remove any remaining source material after removing the building. And eventually we received a no further action from the regulators. Next slide, please. So this is kind of a cost comparison. The top line, the blue dots, shows the $8 million pump and treat with no end in sight, since they had their conceptual site model wrong, CSM, and I assume $15,000 a year annual monitoring. We don't have the cost for operation there. And the bottom line is our cost, which was for the $15,000 per year for monitoring for a number of years until the site was decommissioned and no further action. Next. So some of the other costs that I didn't put into this graph, both the original consultant and Dragun had initial remedial investigation likely. There was going to be litigation that was likely because the way the initial interpretation was that our client was contaminating the subdivision next door. They would have to have cleaned it up. And then there was a decommissioning cost that both of us had. Next slide, please. Our other costs were the initial remedial investigation and decommissioning. So essentially, we saved about $8 million. And the only reason that we could do that was because we figured out that the previous consultant had extremely misinterpreted the hydrogeology and the contaminant transport. Next slide, please.
All right, thanks, Mike. Thanks, Alan. Hello, I'm Chris Perry at Dragun. I am going to talk about the second case study, which is relating to a gas bar, remediation, a gas bar in Ontario, where there was a significant release of gasoline. And one of the first things we did when we became involved in this project was to sit down with the client and understand what the key issues were and what their goals were. And number one was to protect their brand image. There was a concern about impacting a third party because at this point, they already knew that there was contaminated groundwater that was likely moving towards other parties. We also had an issue with vapor intrusion with complaints in the building on the property itself. We also had some conditions relating to LNAPL, which is free product that was in the ground below the site. And the client wanted to do everything they could to keep the business open or come up with a remedial plan that was had the least impact on their business. And the challenge to Dragun was to deal with all of these above issues in a cost-effective manner. So the first thing we had done is there was some discussions about pump and treat, about dig and haul. And the reason why that came up is because the previous consultant that was working on there before we became involved, this was kind of their go-to plan, is just dig everything up. And of course, when you're digging up contaminated soils or and then pumping out product and pumping out water, you're essentially closing the entire operation. So here's an active gas bar in a very busy area, and they'll have no revenue for at least 2 months while all of that remediation work is going on, to the tune of $1.5 million. So that's a pretty significant cost at a gas bar to spend for remediation. So the client wanted us to get a better understanding of the conditions on the site, So this is basically how the site was laid out. We have the gas bar. North is at the top of this map. Groundwater is moving in a westerly direction. It's going towards a restaurant and a bank. These buildings have basements. We're in a very active commercial area. We had a situation where we needed to understand that the fuel system had been repaired and that was no longer going to add any more hydrocarbons into the subsurface. So there were petroleum maintenance people that came in, found the problem at the gas bar, which was a leaking fitting on the underground piping, and that was repaired. Then we took some further steps into evaluating and reviewing previous reports that our client gave us. What we found is there's no previous conceptual site model. And the client or the previous consultant really didn't look into trying to understand what were the most appropriate standards to be applied at this property. So we did that analysis and determined that we had a non-potable condition. So that allowed us to use less stringent standards for the purposes of remediation. And we also found data gaps in the previous work. As Mike had mentioned, we have to get our hands around the problem. They really didn't yet. They hadn't done any horizontal, had not completed the horizontal delineation, and there was still vertical delineation that needed to be done for the dissolved phase plume in the groundwater, and also for delineation of the extent of the product that was on site. So what did Dragun do next? We used our typical approach where we identified these data gaps and we went out and conducted the remedial investigation to try and put our hands around everything horizontally and vertically. And then we took all of that information and built a robust conceptual site model. We certainly believe that we have to understand the problem and we have to have a very thorough understanding of what areas need to be remediated in the subsurface, which then allows us to make the appropriate decisions moving forward with remedial options. So what were the conditions on this site? They were not that unusual or complex. So we had a site that basically mostly was sand. Water table was shallow, 2 meters or 6 feet below grade. We had product that appeared to be just around the tanks, pretty much not far from where the leak occurred in the fitting, in the piping fitting. And we confirmed that the groundwater flow was in a westerly, southwesterly direction. Did some cross sections, which adds to our conceptual site model, trying to look at the distribution of the chemicals here in a vertical profile. Certainly we had BTEX and PHCs in the groundwater. We had some high concentrations in the soil in the smear zone. We had product. Groundwater flow direction was better understood, but we had wells that were right at the property boundary, which is kind of in the center of this cross section. There were sentinel wells installed where we were starting to get detections of hydrocarbons. So there was a very real concern here that this plume was heading off site and was going to impact another party. Not only was there that concern, the other concern was that there's basements there and we would be looking at a potential vapor intrusion issue. So we had all kinds of issues here. And then we had to take a look at a little more details at the groundwater because we started to notice some problems just south of the gas bar. And what we found is there were some utilities that were buried at the depth or very close to the depth of the water table. And depending on seasonal fluctuations, that trench that had been excavated and backfilled for the sanitary sewer played a bit of a role in the distribution of the hydrocarbons in and around this property, which was something that had not been previously addressed at all. So the key considerations we talked about, we had the shallow water table, a sandy soil, the product was only around the tank nest. We had a smear zone around the tank nest and a little bit outside of that tank nest. We understood what hydrocarbons were present. We did some in-well slug tests, single well permeability tests, and determined the hydraulic conductivity. We could then use that information to determine the groundwater velocity. And we also knew what the flow direction was, and we also looked at potential for chemical retardation. We made the assumption that the plume velocity and groundwater velocity would sing. So we had to go back and think about our client goals. And the key thing was dealing with the adverse impact to the employees on the property. Is we had to take that vapor intrusion problem out of the picture. We had to make sure that the business stayed open. Like I said, this is a very active area, very commercial, busy area, pretty high population, lots of gas being sold to the tune of hundreds of thousands of liters per month. And we still had to look at a cost-effective approach. So we looked at multiple remedial options. And one of the key things we always do at this point is we always look at natural attenuation. Mike had talked about how monitoring was applied on his case study. And here we always kind of look at that to say, can we do monitored natural attenuation? And we ran some simplistic computer models, and that revealed that natural attenuation was not going to be adequate for reducing the concentrations in this plume. Basically meaning we had to do some type of remedial activity to reduce those hydrocarbon concentrations in the subsurface. So then we looked at 3 options. The first one I talked a little bit about was the physical removal, the dig and haul. Many of you may know what that means, but it's a traditional go-to approach of just digging up pretty much a large portion of the property down to 10 or 12 feet, digging it all up. And in the process of doing that, you're taking out the underground storage tanks, the fueling system, the piping, all of the associated infrastructure, and the gas bar certainly is not operating. The in-situ chemical oxidation option was reviewed and evaluated and scored high in the way we score our options, and was less intrusive, lower cost, will still meet our project goals, and we believed at the time when we assessed everything, it would meet all of our clients' objectives. We also looked at enhanced bioremediation. Costs were a little closer to the in-situ chemical oxidation, but we decided to go with the chemical oxidation because we felt that there was a higher level of confidence that we would achieve all these goals that we had outlined with our client. So we selected the chemical oxidation. We also did removal of the free product with some physical pumping. So we used a pumping apparatus to remove the product, and we ended up recovering about 1,500 liters of product. And once that was gone after about 18 months of pumping, it never returned. And we injected about 6,800 kilograms of chemical oxidant remedial product. And we did these injections over a couple events. And in the end, we were successful and able to decrease the concentrations in the subsurface to meeting the criteria and the standards that were set for that site, the applicable standards. And the product, the free product, LNAPL, was also removed. So we went back, and now it's been a couple of years since we've completed this project, and we've looked at this graph as to where we would have been with the options. And certainly with the option that was put on the table way back at the beginning of this project, that was 2009, 2010, we were looking at costs starting in $1.5 million, which then increased because there would be monitoring requirements, at least for several years, I assume 3 years, until we would meet the standard. So you're looking at $1.655 million to remediate a gas bar. Not really feasible for most people at a gas bar. Then we looked at what the actual costs were for our project, and in the graphic, the lower line represents the actual true costs for this project, taking it from at the end of year 1 all the way out to about 2017, 2018, when we had a final project cost of $638,000. So pretty much $1 million in savings on this by going with an option of just in situ, and the entire time that in situ remediation was being done, we never once shut down the operations of the gas bar. So we had no impact on the revenue. We removed the indoor air quality concerns because the product was gone, and basically we remediated all the media in the subsurface. Product was gone. Groundwater monitoring data at the Sentinel wells, as we continued to monitor for 4 to 5 additional years, at the end, we never found concentrations of hydrocarbons in those Sentinel wells exceeding the standards. And basically that means we had no third-party issues to deal with. So we ended up, as I said, total remediation costs were in the range of $650,000. So 8 years from the time we started this project with this in situ method, we ended up receiving a letter from the regulator in Ontario, which is the Technical Standards and Safety Authority, and they concurred with our conclusions that it was no longer necessary to continue with any remedial actions on the site.
Thanks, Chris, and welcome everybody. My name's Jeff Boland. I'm Vice President of the Dragun Corporation. I've been here too long, 31 years now. And this site was circa mid-1990s when we got involved. And our client was a metal plater that had been operating since the mid-1950s. It was a RCRA corrective action site, and for our non-US attendees, RCRA regulates sites with hazardous waste activity, and RCRA corrective action is a site where a release has been identified and is being addressed. And for I think a lot of the people on the webinar, you're probably aware that RCRA sites and RCRA corrective action sites have a lot more scrutiny and a lot more regulatory hurdles and structure than a CERCLA site type of cleanup. And the site was under US EPA lead, since it's always easier with more regulators at the table. This one also had a very involved MDEQ representative out of Michigan. And the RCRA corrective action activity had started with the closure of a plating waste lagoon approximately 10 years prior to us getting involved. When we did get involved, we had recently worked with this client on a different site and helped them save a lot of money on a TCE cleanup. And although we had not been involved at this site, our client retained us to peer review work completed to date, because it just seemed like it was going on, as I mentioned, 10 years prior. And additionally, they just received another work plan from their consultant to do another round of, in their words, expensive investigation, and they wanted a second opinion. And even further of their concerns was that in discussing with the regulators, pumping and treating of contaminated groundwater had come up, and they were concerned about long-term costs and if there might be some other options. So this case involved really a couple of things that have been discussed already, but the three main cost savings came up by negotiating cleanup criteria that offered more flexibility in how the site was addressed. We were able to obtain a delisting of the waste material that was removed from a hazardous waste to a non-hazardous waste. So understanding those regulations. And then ultimately we used ecological risk and groundwater modeling to avoid the groundwater pump and treat. So to put a little perspective on the issues at the site and what was driving some of the regulatory concerns, the key focus became contaminated groundwater from two landfilled areas on the property, and those are represented by the two red stars that you see there, number 1 and number 2. And complicating things was the slightly purplish star off to the left of this slide, and that was a former village dump, and the fill area of number 2 and the village dump kind of crossed over and overlapped each other. So that complicated things a little bit with respect to that concern. Additionally, there were 2 water wells represented by the blue dots with the W's. There were 2 water wells up by the plant that were used both for production and for drinking water at the site. And what turned out to be initially a hurdle, but sort of our silver spoon in this, was the property was abutted by a wetland, an intermittent stream, a small river that was designated a cold water trout stream that ultimately discharged to another river further to the west of this property. And from a site closure perspective, and a regulator perspective, there were just a number of concerns that had to be addressed at the site. And so during our peer review, one of the first things that we noted was that there could be an opportunity to utilize, and I think Mike brought up that regs change and things. Well, in this case, the state of Michigan had just updated or changed their regulatory scheme. So there was an opportunity to utilize these newly enacted state cleanup criteria, which would help us frame the endpoint of the project. And RCRA corrective actions at this time in the mid-90s typically involved nature and extent definition to non-detect for contaminants, and the US EPA was certainly driving towards this non-detect delineation. So if we were to leave contaminants in soil or groundwater, that usually required undertaking a full human health risk assessment for the site under RCRA. In this situation, as I mentioned, Michigan had recently promulgated risk-based criteria that included industrial scenarios. So our client decided to pursue this, and we met with the US EPA at the site and talked about it a bit. And we, and I kind of say we in quotations, because we, along with legal counsel, were successful in negotiating the use of these Michigan risk-based criteria for the site. And this allowed us to forego the full human health risk assessment at the site. It allowed us to decrease the amount of investigation to delineate the site, and allowed us to leave certain levels of contamination in soil and groundwater without active remediation. And I'm not sure how much of a role it played, but when we were walking the site with the US EPA, the US EPA representative asked me if the Dragun Corporation was affiliated with Dr. James Dragun. And I said, well, he's our founder, and his office is just a few steps from mine. The US EPA guy said, well, I've got a copy of his book on my desk, and I use it for a reference. And so I figured, click that one in my memory, and I said, this should be a wonderful thing, and we should have very little pushback from the regulator. As I mentioned, much of the focus initially centered on two areas of the property where the plating waste had been landfilled before RCRA came into play. And based on geophysical testing and on test pits, it was estimated that between these two fill areas, there could be about 7,800 cubic yards of waste material. And the majority of the fill material was in these two areas depicted by the stars, and defining that 7,800 cubic yards also, as I mentioned, required us negotiating a little bit of how far we had to excavate relative to where the municipal filling activities overlapped. And the US EPA was certainly looking for source removal of these materials. And given the site conditions, it made sense to remove the fill material. However, under RCRA, this could be tricky. The main chemicals that were associated with these wastes were cyanide, copper, and some TCE. And from a strict RCRA interpretation, these plating wastes would be listed hazardous waste, in this case from a non-specific source, and mainly under the listing numbers of F006 and F008. And as such, as a listed waste, it would be hazardous regardless of its characteristics. And as such, very expensive to dispose of. And what we were able to do here is show that these wastes did not exhibit the characteristics that made them a listed waste under those designations. And again, in tandem with legal counsel, we were able to delist the waste under a one-time exemption. And ultimately, it ended up that we excavated about 8,600 cubic yards of waste, but they were disposed as a non-hazardous waste at a type 2 landfill at a cost savings of over $1 million on that source removal and of that waste disposal. Avoiding pump and treat at this site ended up taking a few steps. And first, using monitoring well information and groundwater modeling, we were able to defensively show that the plant itself was not a source, that the main source of groundwater impact was indeed from infiltration of precipitation through these fill areas. And further, we were able to show that the on-site water wells were not a risk from contaminated groundwater. And finally, that the main receptors were in fact the surface water bodies from venting of contaminated groundwater. And that helped us get our arms around the situation, as Mike talked about. So armed with kind of this information and following the source removal, we were able to negotiate that the main focus of any corrective measures should be focused on the surface waters. And so looking a little bit at that, this slide shows a cross section of the property that cuts from just south of the plant through the larger area of the fill towards the river, so through that number 2 star. And from a conceptual site model perspective, the overall property sits on an organic rich sand with a relatively shallow water table that you can see in the cross section. And as discussed, relative to potential sources, the conceptual site model included the fill areas and the plating system or facility initially. And relative to potential receptors, the conceptual site model included at one point the drinking water wells, and then the wetlands and the surface water bodies where the groundwater was discharging. But looking at the groundwater contouring and monitoring well data, we were able to confidently show that the plant area was not a significant source, and that the main source of groundwater contamination was coming again through these infiltration through the fill areas. And through that groundwater contouring, also able to show again where it's coming onto the site in that upper blue line area. Those water wells are just above that arrow, that there's clean water coming to those wells. And you'll notice a little bit in this particular slide, there's some very steep groundwater contours along the right side of the slide. And just so you don't think we had contouring gone wild like Mike talked about, those were due to where this river starts at the bottom of the slide. It's dammed up at the roadway, and there's a large lake to the right of this slide that causes that steep groundwater. But as the groundwater flows away from that influence, we see that it flows much more along a southwesterly path. And we were able to provide even more definition to this groundwater just looking at the contouring by using groundwater modeling. And we used a mod flow model to better predict where the contamination from specific wells was going. And these red lines that you see on this slide show particle tracking from known contaminated wells. And these lines show where the most contaminated groundwater was discharging. And we also used a FlowTrans groundwater model to show that the impacted groundwater in fact discharged to these water bodies and mostly to the river and did not underflow the river. And the regulator had a concern that the plume of contamination may be going under the river. And we were able to show that indeed it discharged to the river. And that gave us an endpoint of how far we had to be concerned about that contaminated plume. And since we knew where the groundwater was discharging, we ended up conducting an ecological risk assessment of the surface water and the wetland ecosystems. And the ecological risk assessment concluded that the impacted groundwater, although may have been venting to the surface water bodies for conservatively up to 45 years, only a minor effect was observed, and that was in a small area of the intermittent stream mostly, again, down gradient to the fill area. And the effect was isolated to this small area, most likely due to copper in the sediments. And the risk assessment also concluded that removal of the impacted sediments and this minor effect would probably be more disruptive to the ecosystem than leaving them in place. And ultimately, the US EPA agreed with this conclusion, and we were able to leave those in place and only do monitoring. So ultimately, we were able to limit the amount of investigation utilizing the use of recently enacted cleanup criteria that were already risk-based criteria. And we conducted focused source removal as a non-hazardous waste, and that was huge in cost savings. And then we were able to avoid the installation of a groundwater pump and treat, and instead just conduct monitoring of groundwater quality at a limited number of locations because we had focused where the contamination was going. And all this was at a significant cost savings to the client. And this graph shows from a financial perspective somewhat a reflection of what happened here. And the red line at the bottom reflects again, basically what we did with non-hazardous excavation and disposal, and then using the ecological risk assessment, limited industrial risk-based closure, the numbers. And the blue line shows if the waste would have had to been initially handled as and disposed as a hazardous waste, significant jump, and then the capital cost of putting a pump and treat system and operating that system for a significant amount of time, typically 30 years at a minimum, but would be till you got clean. We were able to avoid that for the client. So significant cost savings from that.